So this might be a very strange video for me to make, but this stuff I'm interested in. The title is The Mysteries of RS-232. Success in this field requires connections is the subtitle. This is written by Bruce Eckel. The editor introduces the article by saying asynchronous serial communication is definitely one of the weirder parts of personal computing. Although RS-232 is a standard interface, you can't just plug things together and expect them to work. Okay, so now Bruce jumps in with, in this article, I'll discuss my strategy for cabling problems, talk about RS-232 on the IBM PC and its clones, try to dispel some of the mystery of communications protocols, and otherwise entertain you. In serial communication, you force all the information through a single wire, one bit at a time. Sounds strange, doesn't it? Instead of each bit in a byte having its own wire, as on a parallel printer port, each bit has to wait its turn on a single wire. There are two methods for communicating serially, synchronous and asynchronous. In synchronous communication, there are two signals, data and clock. Because of the clock, which tells the receiving end when the next bit is valid, there is no need to pause between bytes to reset both the sender and receiver. Thus, there are no stop or start bits. In asynchronous communication, by far the most common mode, only the data is sent. First, both ends have to agree on how fast the data is sent, the baud rate. Then there's pause between characters, the start bit at the beginning of the character, and the 1, 1.5, or 2 stop bits at the end. By keeping track of the start and stop bits, and by knowing how fast data is being sent, the receiver knows when to look for each of the 8 or 7 data bits that come between. Figure 1 shows how a byte is transferred. The ones and zeros are logical. They don't reflect the voltage values on the RS-232 lines. So more about that later. When quiet, the line is in marking condition. Parentheses, it's marking time. The first edge of the signal notifies the receiver that a new byte is beginning. To ensure it wasn't just a noise glitch, the receiving device, the 8250 on a PC, rechecks the signal by sampling it several times. After the last data bit, some extra information arrives. If you have parity turned on, then the 8250 adds a 1 or 0 to make the number of 1 bits in the character even or odd parity. If one of the bits was received incorrectly, then the receiving end would notice that the number of ones was no longer correct. If 2 bits changed, then parity checking wouldn't catch the problem. The stop bits arrive last. You can use 1, 1.5, or 2. The stop bits return the line to its marking state. They allow the receiving system some time to take care of things before the next byte starts. The most common configuration you'll probably use is 8 bits. No parity, 1 stop bit. This means 10 bits are transmitted for each byte. So if you divide your bit rate, also known as baud rate, where they should have just wrote baud, by 10, the result will tell you approximately how many bytes per second you will move. For example, at 9600 bits per second, you'll move approximately 960 bytes per second. This number is only approximate, since most file transfer protocols add bytes to the beginning and end of each data block. After a byte has arrived, the 8250 places it in a temporary storage register and sets some flags. If there were unread bytes in the register when the new one came in, destroying the old one, the overrun flag is set. If parity is on and parity isn't right, indicating a noise glitch on the line, the 8250 sets the parity error flag. If you've set up the system for interrupts, this is performed in software by your communications program, a received byte forces an interrupt. Then the interrupt service routine must grab the byte before it's overrun. There are only 3 important wires in serial communication: a line to transmit from, a line to receive, and a ground line You can transmit and receive at the same time. The lines are completely independent. You may notice there are usually 25 pins on your serial connector. That's more than 3. To understand why, some history is in order. So the EIA, which stands for Electronic Industries Association, RS-232C, which stands for Recommended Standard 232C, was developed solely to connect data terminal equipment, also known as DTEs, which are computers, terminals, printers, and other like machines. So this standard was developed to connect these DTEs to data communication equipment, DCE, that is a modem. So it consists of the definition of a set of lines through which this communication takes place and the voltage levels for 1 and zeros through these lines. The physical connection is most often made through either a DB25 or DB9 connector. Check out the pinout and the line names in figure 2. I started this video by showing a picture, so you could always go right back to that. A logical 0 is represented by a signal between 5 and 15 volts. A logical 1 is represented by a signal between -5 and -15 volts. As you might guess, there is also an RS-232B. It uses voltages between 25 and -25 volts. It's worth noting that the standard RS-232 driver chip and receiver chip don't work reliably at plus or minus 5 volts. The Commodore 64 contains simple transistor level shifters in place of these chips. The Commodore's RS-232 interface doesn't work with all serial devices. Now the other handshake and clock lines on the RS-232 interface uses the same voltage levels as the data lines, but their sense is backwards. On these lines, a positive voltage represents a logic 1 and a negative voltage represents a logic 0. Signal generators assume they'll be driving 3K to 7K ohms, thus they have to supply between 2 and 5 milliamps. Most line drivers and receivers are capable of supplying between 10 and 20. Okay, and then he's going to go into cable length. He says it's a tribute to human ingenuity to see how many non-modem things people found to hang on to the RS-232. He talks about another insidious line is clear to send, CTS. He'll talk about a second solution to the flow control problem being software. He says the PC can access via the microprocessor's address line memory cells or I/O cells. I/O addressing has different timing and handshaking than memory addressing. I/O devices generally respond more slowly than memory. Not all microprocessors do this. The Motorola 68000 family, used in Macs, Ataris, Amigas, and many Unix machines, puts all of its I/O in the memory space. This is called memory mapped I/O. The 68000 has special handshake lines for slow memory or peripherals. The status pins on the 8086 or 8088 microprocessor tell the rest of the system whether the next access will be memory or I/O. High-level languages also have some method of specifying I/O. The language BASIC uses the in and out commands. Turbo Pascal uses the port array. Turbo Prolog uses the port byte predicate. And Microsoft C uses INP and OutP. Okay, and I typed it correctly there. When a communication program attempts to transfer a large amount of data, for instance a file, over a serial length, it runs a risk. It's not unusual for noise or other problems to change bits as they sail across the line. For file transfers to be dependable, the transfer program must be able to determine whether there's an error, and if so, correct it. Most file transfer protocols break files up into blocks or packets. This way, you don't need to retransmit an entire file if there's an error. Data is usually surrounded by information which says a packet is coming, this is its number, here's the data. One of the earliest microcomputer protocols is Ward Christensen's X-modem. X-modem divides a file into packets containing 1, the state or the start of header character to indicate the beginning of a packet, the sequence number of the packet, both normal and its one complement, 128 bytes of file data, and 1 byte of checksum, or the check value, which is calculated by simply adding all the data bytes together as they come in, throwing away the carries. Although by no means perfect, X-modem is probably the most commonly used protocol. An early flaw, a checksum can miss errors, has rectified with the addition of a cyclic redundancy check, CRC, for the check value. CRCs are more complicated but much more reliable, but you must often specify X-modem checksum or X-modem CRC. The Y-modem transfer has its own protocol, but will use X-modem if that's what the other end is using. Z-modem, WX modem, and others keep popping up. Usually, what's best is whatever the other machine uses. I've looked at a number of domain shareware communications programs, and I think my favorite is Shareware's Procom. It's mature, it seems bug-free, it supports most popular file transfer protocols, it emulates a VT100 terminal, which is convenient for connecting to minis and mainframes, and it's easy to use. The only problem with most of these protocols is they were developed on microcomputers, so many of them can only be found on microcomputers, though X-modem is often found on Unix systems. Columbia University set out to smash the communications protocol bug once and for all with Kermit, which was designed to work on all computers without regard to size. This was an ambitious project, but it seems to work, and it helps that all the source code is public domain. Kermit negotiates with the other end to establish the communication parameters. This is clever since it allows extensions to the protocol without disturbing existing installations. And then Bruce Eckel will end this particular article by saying, someday there's a lot more to writing a communication program than I can cover here. He suggests we check out Joe Campbell's superb C Programmer's Guide to Serial Communication, but he does plan to do some kind of experiment with it in the coming months, so stay tuned.